Last lesson, we looked at using Dijkstra's shortest path algorithm to plot the best path home for our character CJ. Dijkstra's shortest path algorithm helped us find the shortest path to all other nodes on a map. But this may be too much for our needs if we only require the shortest path between 2 points and not every point. Using Dijkstra's is not too taxing to work out on a small map. It's more difficult to work out on a map with more nodes, and this is because we need to calculate the distance to each node even if we don't need to get to that node. A map of a city or between two cities can have thousands or millions of nodes. This would make it less feasible. The A-star algorithm adds heuristic values to the map. This helps us develop an educated guess. This could mean an estimated distance from start point to end point, possibly by drawing a straight line using the latitude and longitude. It could be added live data, such as traffic data, which can be in the form of a number of cars on a particular road or path. Or it could be added live data such as news of accidents or roadworks. The good news is that the heuristic values are always given to you in an exam. You don't need to see how this is worked out. This is extra information alongside the cost of each given path, but think of this as an abstracted value which is given to you. You don't have to work it out. With Dijkstra's algorithm, we were given a cost of each path from one node to another. The A-star algorithm also adds heuristics, which, as mentioned before, are the estimated costs from a node to the final destination node. Here you can see the heuristics shown as a value under each node. The A-star algorithm in theory produces a faster calculation of the best path from the starting node to the destination node by using heuristic values given to help out estimate the best path without having to visit each node. As you can see from this sample model, the A-star algorithm sometimes results in not all nodes being visited. In theory, it helps to find the best path without having to do so in some cases. Similar to Dijkstra's algorithm, we're going to plot the cost of each node into a table. This table also includes the heuristic value and the cost of the heuristic value alongside the distance between nodes. The heuristic values are given to us, so we may as well add them to our table. Again, similar to Dijkstra's algorithm, we are adding the cost to travel from our starting node as 0 because that's where we're starting from. As before, distance traveled to each location is marked as infinity or a very high number, until we visit that node, and we can reduce the cost if the cost is lower. So we now work out the cost of connected nodes to A using the distance and the heuristic values. So the cost of traveling from A to B is 5 and then 7 for the heuristic value, which equals to 12. So we add that into our table. If we do the same again from edges A to C, we know that the cost is 2 and the heuristic value is 3, which equals 5. And the cost from A to E is 6 with the heuristic value of 2, which gives us a total value of 8. Since we've worked out all the possible paths from A to its neighbors, we can mark A as having been visited. We now select the unvisited node with the least cost in terms of distance plus heuristic value, which is C. We can see that in our table here, C being the least value. Since nodes D and F are listed currently as infinity or too high or unfeasible, we're going to compare B, C, and E. B, C, and E. And we conclude from this that C is the best choice. So again, we're going to repeat the process of working out cost of visiting the unvisited connected nodes. In this case, it's E and F. The cost of traveling from C to E is going to be 2 plus 3 plus the heuristic value, which is 7. This is lower than the current value of 8, which is what we had in our table. So we're going to cross out the original values and replace them. The cost of C to F is going to be 2 plus 8 and then the heuristic value of 0. This is lower than the currently listed infinity, so we update this to 10. And as a result, we can now mark C as been visited. We repeat the process of working out the cost of visiting the unvisited connected nodes again, and the node with the lowest connected to C is E. Therefore, we visit E next. The cost of visiting F from E is going to be 2 plus 3 plus 4 with a heuristic value of 0, which equals 9. This makes this vertex or path less costly than the previously worked out value. Therefore, we update our table again. So we change it from 10 to now 9 altogether. And we've updated our previous node from C to E. The other node connected to E is D. So the cost of visiting D from E is going to be 2 plus 3 plus 6 and the heuristic value of 5. This equals 16. Now that we've visited E, the two connected nodes to E are D and F. The node with the least cost to visit from here would be F. So this becomes our next node. Since F is our target node or destination, we can say that we have found the path with the least cost and also mark F as visited. We can now work backwards and mark our path as FECA or ACEF in the correct order. And the cost of that we know is 9. So using the A-star algorithm, we have efficiently found the least costly path from our starting node to our target node without having to visit every node. This is an example of how the A-star algorithm is more efficient than Dijkstra's shortest path algorithm. So we know that with Dijkstra's, it's more difficult on a map with more nodes. This is because we need to calculate the distance to each node, even if we're not going to get to that node. So in this instance then, in most instances where the map is bigger or the graph is bigger, A-star algorithm is more efficient. So again, as always guys, please download the worksheet, try the questions out and see if you can work out the best path for CJ in this next one.